In Module 2, we're going to talk about the chemical foundations and chemical nomenclature from Chapter 3, Section 12. So we're going to start off with 1-2. 1-1 is not applicable to our discussion. So we want to be able to discuss the steps in the scientific method, define the following terms of theory, law, hypothesis, experiment, and observation, discuss the difference between models and reality, and recognize some natural laws. So what is a science? A science is the application of scientific method to problem solving. Now the scientific method is shown in the figure, and it starts off with an observation of a problem. You have to see that a problem exists. You propose an explanation of that problem, that is the hypothesis, and then you perform an experiment. Now this is an iterative process, meaning you observe, you hypothesize, you experiment, and you start all over again. A lot of times teachers will tell you that if you continually test your hypothesis, eventually you'll end up with a theory. Well, that's not exactly true. A theory is actually a model that comes from several different experiments. The theory attempts to explain and predict behavior. So explain and predict. And that's the difference between a model, a theory, and a hypothesis. A hypothesis is a proposed explanation, but a theory explains and predicts. Now, you can make those predictions and then test them, and again, this is sort of an iterative process. You come back and you modify the theory as needed. One of the things that we need to make abundantly clear is that in science, theories are simplified models of reality. They are not reality. They are models of reality. And because they are models, they're not exactly true to reality, and they are subject to all the problems that humans create. In other words, they are fallible. They are subject to interpretation and debate, and even sometimes being completely disregarded. There are several theories that have fallen out of favor as new informations and better theories, better models have been constructed. Along with theories and hypotheses, you may have heard of the term law. A law is different than a theory or a hypothesis in that a law, I like to say, is just is. It's something that is true, and we may or may not know why it is true. So, for example, gravity is a law that is true. We do not have a theory of how gravity works. So the steps in the scientific method, the ones we usually deal with on an everyday basis in the chemical laboratory, is the first part that was in the green portion of the figure, where we make observation, we formulate a hypothesis, and we perform experiments. Now, observations come in two types. They can be qualitative or quantitative. Qualitative talks about the quality of something, whereas quantitative involves measurement. Okay? A hypothesis is the possible explanation for an observation or an answer to the problem. And when you gather experiments, you test the hypothesis. And the way that you would test a hypothesis is you want to carefully control all the possible variables that you can and test one thing. And then come back, make new measurements, make new observations, maybe revise your hypothesis, and experiment again. All right, so theories, again, are models that are used to explain and predict behavior. Explain and predict. That is the key to a theory. It is a model. Some theories that we are going to talk about are atomic theory, quantum theory, and you may have heard of the theory of relativity. Very famous, put forth by Albert One Mug, or Albert Einstein. Get it? German One Mug, Einstein. Those are different than laws. These are observations that just are. So, for example, gravity. We will deal with the conservation of matter. Matter can neither be created nor destroyed in a chemical reaction, or the conservation of energy. Energy can neither be created nor destroyed. So that is the difference between the hypothesis portion, the theory portion, and then the law portion. Section 1.3, we're going to talk about the contributions of some very famous scientists in the development of modern chemistry. So chemistry as a science has a vast and fascinating history. The word chemistry actually comes from Egyptian, the word alchemica, which eventually became alchemy, and then alchemy became chemistry. We're not going to talk about a whole lot of that vast history because it's been around for thousands upon thousands of years. But there are some people of note that we do need to talk about. The first one is Democritus. Democritus was a Greek philosopher, and he proposed the concept of the atomos, or the atom. Basically, it was the fundamental building block of all matter. And the argument he proposed is similar to the idea of if you take a piece of paper and you tear it in half, and you tear the half in half, then you tear the quarter in half, then you tear the eighth in half, and so on and so forth, you'll eventually end up with the smallest bit of matter that you cannot break. That was the atom. We move along from the ancient Greeks to the 15th or 1600s to Robert Boyle. And Robert Boyle is known for his quantitative analysis of gases, hence known as Boyle's law, a pressure to volume relationship. And he was the one who started putting chemistry a little bit on a more scientific bent in the fact that he was making careful measurements. A lot of these times it had been, up to then, it had been more about the secrecy, the alchemy behind it, where it was recipes and potions and such. Think potions class in Harry Potter. But he started making very careful quantitative analysis. Then we come to Joseph Priestley, and he discovered oxygen and explained how combustion worked, even though he was wrong. That is the whole theory of phlogiston. As I said, some theories have been thrown out in favor of better theories. I'm not going to talk about phlogiston, but it's a very interesting path that actually set us back quite a bit of time. And then finally, Antoine Lavoisier in the 1700s, who is the father of modern chemistry because he applied the most careful measurements to chemistry, and he really brought alchemy into chemistry. And he could have done a lot more, but he lost his head in the French Revolution because he was a French nobleman. All right, in Section 4, I want you to be able to state the following natural laws and to be able to give examples or explain those laws. Now, chemistry has fundamental laws that allow it to be a science. The two most important are the law of conservation of matter, which says that matter is neither created nor destroyed in a chemical reaction. It only changes forms, which is really important because that means that in a chemical reaction, all of the atoms I start with also have to be in the end. So I can't lose or gain atoms. I can only make them rearrange. The law of conservation of energy states that energy is neither created nor destroyed, that it can only change forms. And we've already seen this in the review chapter when we talked about kinetic energy and potential energy. Another very important law is the law of definite proportions, which states that a compound always contains the same proportion of elements by mass. And that is to say that water, which we know has the formula H2O, will always contain the same ratio, 1 gram of hydrogen to 8 grams of oxygen by mass. If you have a substance that contains only hydrogen and oxygen, and it does not contain that ratio 1 to 8, you don't have water. So for example, another formula, or another substance that contains only hydrogen and oxygen, contains 1 gram of hydrogen to 16 grams of oxygen. This is what we know as hydrogen peroxide, or H2O2. The other law is the law of multiple proportions, and that states when two elements combine to form a series of compounds, the ratio of masses that combine with one element to 1 gram of the other element can be reduced to whole numbers. An example of this is something like, for 1 gram of carbon, I can have 1.33 grams of oxygen. And for another compound of carbon, I can have 1 gram of carbon to 2.66 grams of oxygen. And if I ratio these, 1 gram of carbon to 1 gram of carbon, that is equal to the 2.66 grams of oxygen over the 1.33 grams of oxygen, that is equal to a 2-to-1 ratio, hence the simple whole number. We can see that above, where we had H2O and H2O2, 1 gram of hydrogen to 1 gram of hydrogen, 8 grams of oxygen to 16 grams of oxygen. And it's the law of multiple proportions that actually allows us to determine chemical formulas like H2O and H2O2. In Section 5, you need to be able to state the postulates made by Dalton in developing the atomic theory, and to state Avogadro's hypothesis. Now, John Dalton was a Quaker, and he was a very interesting fellow in his own right. There's a lot of interesting things about John Dalton, including his colorblindness and his willingness to actually experiment on his students. However, what he's most famous for is two things: his atomic theory and his law of partial pressures, which we will talk about in the gas chapter. But Dalton's atomic theory, basically he took all the time to organize the knowledge and propose a theory. And he said that each element is made up of tiny particles called atoms. Okay, so he took Democritus's atomos and restated that. And then the important thing is he stated that atoms of a given element are identical, and that atoms of different elements are different than each other. And that's really important, because that means that each atom of hydrogen is going to be identical to every other atom of hydrogen. And he also stated that chemical compounds are formed when atoms of different elements combine with each other, and he also included the law of multiple proportions and the law of definite proportions in there, when he said a given compound always has the same relative numbers and types of atoms. And he said that chemical reactions involve reorganization of the atoms. They are not themselves changed, which is the law of conservation of matter. Now, some of these we know now from a modern perspective that they don't hold up. So, for example, postulate number 2, we know that not all atoms of a given element are identical to each other. We have things called isotopes, which are elements which differ in the number of neutrons within their nucleus. So that one has fallen out of disfavor. There are other things such as the chemical compounds, the same relative number and types of atoms. There are things called non-stoichiometric compounds, which sort of break the rules a little bit that Dalton proposed, but as a basis for starting chemistry, very important. And we also know that we can indeed change atoms. We can destroy matter. We can convert it into energy. So instead of having the law of conservation of matter and the law of conservation of energy, what we have is the law of conservation of matter energy, that you cannot destroy matter and energy. You can only convert energy and matter. So it's not a perfect theory, but it is a very good starting point. Some other notable work is that he prepared the first atomic weight table, and he worked on making symbology for reactions. So here is one of his symbol tables, and this is really important because until Dalton's time, the terms were not agreed upon. What people used for naming things was different from town to town, from person to person, from alchemist to alchemist. And so trying to standardize and codify the symbols was very important. He was also colorblind, and he worked a lot on color perception, hence he experimented on his students and their perception of color. It was a very interesting story, which I don't have time to go into right now, but if you want to know, just ask. All right, and then the last thing we have to talk about is Avogadro's hypothesis. Okay, Avogadro was an Italian scientist. And here's Avogadro right there. Now, we know that Avogadro's number is very important in chemistry. We saw that in the concept of the mole in section 10 of the review chapter. His hypothesis was that equal volumes of gases of the same temperature and pressure contain the same amount of particles. In other words, if you have twice the amount of stuff, you need twice the volume in which to store it. Now, this led to the discovery of diatomic elements by Gay-Lussac, and it also confirms the idea of chemical reactions rearranging atoms. So if I take hydrogen and oxygen, okay, which 2 volumes and 1 volume, I should make a 3 total volume of gas, and that is indeed the case. When I just mix hydrogen and oxygen together, I do get 3 volumes. That is Avogadro's law. But if I cause a reaction, if I react hydrogen and oxygen, I end up with 2 volumes of water. And that means that those elements, hydrogen and oxygen, had to have been diatomic in order to form water. Similarly, 1 volume of hydrogen and 1 volume of chlorine leads to 2 volumes of HCl. So that is Avogadro's hypothesis, and the concept of the mole, as we talked about in the review chapter, is immensely important in chemistry. Matter of fact, chemistry would not be chemistry without the concept of the mole.